Hi everyone, I'm Daryl. I'll be presenting a self-knowledge distillation CNN-LSTM model to predict disease outcome with longitudinal gut microbiome data. So gut microbiome are all the microbes in your intestine. They usually have a lot of positive functions, including energy recovery from metabolism of food, protection from pathogen invasion, and regulation of the immune system. So in previous methods, in traditional methods, machine learning models were used to predict disease outcome from looking at gut microbiome data. So they are single time point. They only look at one single time point. And it's usually very hard to model complex distribution with machine learning. Because of that, it's also easy to get a higher performance with a limited amount of data, with little data sets. But gut microbiome data are dynamic in nature, and it has a lot of temporal information. If we just look at a single time point, we are not able to get a lot of information out of it. So instead of machine learning, we'll look at deep learning. Deep learning can model complex distribution much better than machine learning. It's easier to apply to temporal changes, and we can combine several applications into one network. But the challenges for this is that deep learning requires a huge amount of data set, and there's a lot of missing information along the time point of different subjects of the gut microbiome data. And single time point in a gut microbiome tend to not contain enough information, as the temporal information of the gut microbiome has more information. So the solution for this is that we're going to use self-knowledge distillation or transfer learning to solve the limited amount of data set for deep learning, since deep learning performance is much better with a huge amount of data set. But in gut microbiome data set, there's a limited amount of data available. So we'll use self-knowledge distillation to prevent the performance from deteriorating. We're also going to use imputation and padding to resolve the missing time points. For the two different padding methods, padding in sequence, we're going to pad zeros in the missing time points. In this case, week 4 and week 12 are missing, so we're going to pad them at 0 and feed them as a whole into the network. But for the normal padding method, padding and masking, we'll ignore week 4 and week 12. We'll just feed the available time points to the network. We'll evaluate our model on PROTECT study and dipigment study. So for our first distillation method, in this case, we'll use 3 different loss functions. One loss function to minimize the distance from the final prediction and the ground truth labels, and 2 other loss functions, KL divergence and L2 loss, to minimize the feature latent space between the intermediate networks and the final network, and they are all within a single network. And in this diagram, we can see CNN is first used to extract features, and the CNN features are fed into an LSTM to model the distribution, the temporal distribution of the gut microbiome data, and it's fed into multiple feed-forward network before getting into the final prediction. As for the second distillation method, in knowledge distillation, we tend to have a teacher and a student model. Instead of having a separate model, we use the model's previous epoch as the teacher model, and the model's current epoch as the student model. And we'll use the prediction from the previous epoch model as a learning guide on the model's current epoch. This is to prevent the model from diverging too far away from the previous epoch prediction. In this result, we can see that first distillation, second distillation tend to increase the performance of the model, and the best performing model is CNN-LSTM pattern and sequence with first distillation on the PROTECT study in tenfold cross-validation. As for the dipimune, the LSTM pattern in sequence with first distillation achieved the best performance. We also compare our model's performance with other deep learning method that focuses on longitudinal gut microbiome data as well. We'll call them ULSTM as they don't have a name for their method. And our best performing model was able to surpass their model. In dipimune study, our best performing model was also able to surpass their model. We carried out the sensitivity analysis on the different time points. There is no difference in PROTECT study, but there is a difference in dipimune study. If the number of time points seen is less than 4, it affects the performance of the network. CNN-LSTM was able to improve the performance of AUC in both PROTECT and dipimune study without self-distillation, but self-distillation is able to improve the performance in both LSTM and CNN-LSTM in both the study in our evaluation. So we tried transferring, but there's no significant improvements, and data imputation has no significant improvements as well. In future work, we're going to try attention method inside the network and evaluate our method on different studies. Thank you.